Okay, in this video, I'm going to give some basic definitions and examples related to topological spaces. Let's begin with the definition of topology. So, like, what is a topology on the given set? Okay, let's say X is a set or non-empty set, uh, and tau. Uh, so this notation, which we read as a tau, so we are using this notation since this is the notation that you will see in your textbook. Let's say tau is is a collection of the subset of X. So we have a set X and this tau, which is a collection of subset of the given set X. Then this collection tau, then this collection of the subset of X tau it's called a topology. It's called a topology on the given set X if this collection of the subset of X uh, satisfies the following three properties. One of them is the empty set of phi, and then the whole set X, they are the elements of this collection. The second property, arbitrary unions. So arbitrary unions of the elements of tau. Arbitrary union of the elements of tau is in tau. So the second property, it tells you that if you pick any number of the elements of tau, which are the subset of X, if you pick any number of the elements of the tau, and if you take their union, the union must be in tau. And the third one is finite intersections of the elements of tau is in tau. So the third property, it tells you that if you pick finite number of elements of tau, and then if you take their intersection, that intersection must be in tau. If this tau, the collection of the subset of X, satisfy those three properties, the first one is if tau has the empty set and also the whole set X, and the second property, if you pick any number of the elements of tau, and then if you pick if you take their union, the union must be on the tau. And the third property, if you pick finite number of elements of tau, and if you take their intersection, the intersection must be in tau. If this tau satisfy all these three properties, then the tau is called a topology on the given set X. So basically, topology on the given set is nothing. It's just the collection of the subset of given set which satisfy these three properties. Okay, so here the set X, we have this set X, and now we have the topology tau. The set X together with tau is called a topological space. So here X, the set X together with a topology tau is called a topological logical space. So basically, a topological space is the order pair of the given set and its topology. So if you write down X given set and its topology as a order pair, then that order pair is called the topological space. If you want to write down topological space formally, so we should write down like this: the order pair of the given set and its topology. So this order pair is called the topological space. So this is how we supposed to write down topological or denote the topological space formally, but we often use this X to denote the topological space. So instead of writing topological space as the order pair of X and tau, we often use just X to denote the topological space. So when we say topological space X, that means there is a topology a tau on this set. Okay, so far we covered two definitions. One of them is the topology on the given set, and the other one is topological space. Now, next, I'm going to give some examples of topology. First example, let's say I have a set X, a non-empty set X whose elements are A, B, and C. So I have this set X whose elements are A, B, and C. Now let's see the topology on the set X. Okay, so as I said earlier, topology is nothing. It's just the collection of the subset of given set which satisfy those three properties. Now let's consider this collection of the subset of this set X. Let's say the one of the subset is empty set. We know the empty set is the subset of any set. Let's say empty set is in our collection and the whole set X is also in this collection, and then let's say this set singleton set or the set with just one element A, this guy is obviously the subset of this one. Now let's consider this collection of the subset of this set X. Now you can see in this collection we have three subset. One of them is empty set and the other one is the whole set X itself, and then the third one is the is a set with just one element A. And now let me call this collection tau 1. Now let's see whether this collection is a topology on this set X or not. So if this collection is a topology on this set X, then it has to satisfy all three properties. Okay, so what is our first property? The first property is empty set. It has to be in this collection. So obviously you can see the empty set is in this set, and not only the empty set, also the whole set X, which is also it has to be in the collection. Now you can see both empty set and the whole set, they are in this collection or they are in tau 1. So this collection of the subset of X satisfy the first property. A second property, it says that arbitrary union of the elements of tau 1 must be in tau 1. That means if you pick any number of the elements of tau 1 and then if you take their union, the union must be in tau 1. Now you can see here, let's pick two elements. I mean, here we have three elements, but sometimes you can have many elements. So let's say let's pick two elements, phi and x, and then you take their union. If it is if tau 1 is a topology, this union must be in this collection. Now let's see, let's compute the phi union x. If you take the union of empty set with any set, the result is going to be that set, and the x has to be in tau 1, and you can see x is in tau 1. Since it says the arbitrary union, we you can pick all possible elements of tau 1 and then take their union. The union must be in tau 1. So here we took phi and x. Now also you can take phi and then the union of a. So if you take the union of empty set with the set A, the result it has to be A, and is obviously is in this collection. And not only that one, even if you take the union of x and A, it has to be in tau 1. Now you can see here, if you take the union of x with A, x is A, B, C, so the union is gonna be simply x, because A is the subset of x. So when you take the union of the subset of given set, then the result is going to be the whole set. So x is obviously here, and then the other possibility is you can take the union of all three sets here. So union of empty set p with the whole set x, and then the A, this union is x. So you can see here all possible unions of the elements of tau 1, they are in tau 1. So that means this collection also satisfies the second condition. And the third condition or third property is, if you pick a finite number of elements from tau 1, and then if you take their intersection, the intersection must be in tau 1. Since tau 1 has only three elements, so there are only the finite number of elements. So let's say let's take the intersection of those finite number of elements, which means let's take the intersection of empty set and x. If you take the intersection of empty set with any set, the result is going to be empty set. So the intersection of phi and x is phi, which is here, which is in tau 1. And then also if I take the intersection of phi with a, the intersection is again empty set, which is in tau 1. And then let me take the intersection of x with a. X is the a, b, c, element of x are a, b, c, and if you take the intersection of x with a, then the common elements in those two sets is a. So that is the intersection, and you can see the intersection is again in tau 1. And also if you take the intersection of all these three elements of tau 1, because this is the finite intersection. So like I said earlier, if you take the intersection of empty sets with empty set with any set, then the result is going to be the empty set. So in this case, you can see the result is either empty set or the set singleton set A. And also if you take the intersection of any set with itself, is gonna be that set itself. So which I mean that is obviously is going to be tau 1. So that means this collection also satisfies the third condition for the topology. So we can finally say that this tau 1 is a topology. Then tau 1 is a topology, is a topology on X. So this collection is a topology on X. Okay, so this one is a topology. Now let's consider the another collection of the subset of X. Let's call that one, the element of that collection is phi, and then the whole set X, and then let's call it another set is as the AB. Obviously this set AB is the subset of the given set X, and then also let's call the other one is a B. Obviously B, this singleton set is the subset of X, and then let me take one more set whose elements are B and C. So let's consider this collection. And let me call this guy is tau 2. uh, Now you can check yourself this collection tau 2 is also going to be a topology on this set X. You can check its three conditions or its three properties. This collection tau 2 will satisfy those three conditions. That's why tau 2 is also a topology on this set X. Okay, so I'm leaving the checking whether this tau 2 is a topology on X or not to you. But like I said, you can check those three properties. This tau 2 will satisfy all these three properties. Now let me consider one more collection of the subset of X. Let's say the empty set is in our collection and the whole set X is in our collection, and then let's say the singleton set A is in our collection, and then let me take one more set which is a B set with the element B and C. Obviously this is the subset of X, so is also in this collection. And now let me call this set is this collection is tau 3. And you can take this tau 3 also satisfy all three conditions of the topology. So tau 3 is also going to be a topology on the given set X whose elements are A, B and C. So these are the example of topology on the given set X. Now you can see from this example, if you have a set X, you can have more than one topology on the given set. Okay, so we have already seen here three topologies on the given set X. So you can have more than one topology on the given set X. Okay. Now let me take one more set or one more collection of the subset of this set X, and then let's see whether that is going to be a topology or not. Let me let me say empty set is in that collection and the whole set is also in the collection, and then let's call this singleton set A, which is in the collection. Obviously this guy is a subset of the given set, and then let me take one more subset which is the singleton set B, and obviously this is the subset of X. Now let me call this collection is tau 4. Okay, now let's see whether this is a topology on the given set X or not. So if it is topology, then it has to satisfy all three conditions. Now let's see the first one, first condition, empty set, and then the whole set X, they have to be in tau 4. And you can see both empty set and the X, we have taken them in our collection. So the first condition is true. And the second condition, or tau 4 satisfy the first condition. So the second condition is arbitrary unions of the elements of tau 4 has to be in tau 4. Okay, for that one, let me take these two elements, these two singleton set, A union B, and let's take the union of these two sets. Union of these two set is the set whose elements are A and B. Now you can see that this set, this union, after taking the union of A and B, we got this set, but this set is not in the given is not in our collection. So you can see that guy is not in tau 4. That means this collection does not satisfy the second condition or second property of the topology. So tau 4 this tau 4 is not a topology, is not a topology, is not a topology on the set X. So from this example, you can see that all the collection of the subset of given set are not necessarily topology on the given set. Okay. So if you want to check whether the collection is a topology on the given set or not, you need to check all those three properties. All right, so this is our first example of the topology, and now let me give you a couple of more very useful and kind of popular example of topology. The second example, which is called the discrete topology. This is the another example of the topology, which is called the discrete topology. There is a standard name for that topology. It's called the discrete topology. Now, what is the discrete topology? Okay, let's say X is a set which is a non-empty set, and then let's call let's call let's say the let's take let's take the collection of all the subset of X and denote it by tau. So basically, tau is a collection of all subset subsets of X, and which is also called the power set. You guys have learned about the power set in set theory. So if you collect all the subset of given set, then that collection is called the power set. Or so if you want, also you can call this tau is a power set of power set on X or power set of X. Let's say X is the non-empty set, and our collection is the subset of all the the tau is the collection of all the subset of given set, which is equivalently called the power set. Then this collection satisfy all three properties of topology. That means this tau or the power set is a topology on the given set, and this topology is called the discrete topology. Okay, then tau topology is a topology on X, and it is called discrete topology. So basically, discrete topology is the collection of all the subset of given set. So it's kind of trivial example. So if you have a set, and if you take all the subset of given set, then that collection is going to be one of the topology on the given set, and that topology is called discrete topology, I think. Yes, discrete topology. It's called the discrete topology. Let me give you one particular example. So, for example, so maybe is an example inside the example. Okay. So discrete topology is an example of the topology. I'm giving you one particular example of the discrete topology. So it's kind of the example inside the example. Okay. Now let's call X is the set whose elements are 1 and 2. Then the discrete topology on the set X is the power set, which is the empty set and the set X, and then all the subset. Since it has X has two elements, so there are like four subset of X, which are one of them is empty set, other one is the X itself, and the singleton set 1 and then 2. So this set this collection is called is the power set, and which is the discrete topology. Let's say if X is 1 2 is if X is a set whose elements are 1 and 2, then the discrete topology is this set. So this is an example of topology. So if someone asks you, give an example of the topology on the given set, then you can say that the power set of that set is a topology, and there is a specific name for that, which is called the discrete topology. Next example is another uh, uh, famous example or popular example of topology, which is called the indiscrete topology. Indiscrete, or which is also called the trivial topology. All right, in now, so in previous example, we took all the subset of given set, and that collection is going to be a topology, which is called the discrete topology. Now, in discrete topology, it's let's say X is a set, a non-empty set, and then let's take the collection of the subset of X, and this collection has only two elements or only two subset of X, which are the empty set and the set X itself. And this collection also satisfy all three properties of the topology, so that this collection is a topology on given set, and which is called the indiscrete topology or trivial topology. Then tau topology is a topology on X. Sorry, tau is a topology on X, and it is called indiscrete. It is called the indiscrete. It's called the indiscrete or trivial. It's called the indiscrete or trivial topology. Okay, so now we just discuss two kind of popular example of topology, discrete topology and indiscrete topology. We can say that these two topology on the given sets are equal if the set is a single latent set. Otherwise, those two topologies may not be equal. So, for example, let's say your set X is a singleton set. Singleton set means a set with only one element. Let's call is the set whose element is one. Then the discrete topology on this one, then the discrete topology on this set is gonna be all the subset of this set, and the empty set, and then empty set is a subset of any set, and then the other subset of this set is itself, right? So this is the discrete topology. These are the only two subset of this set X, because it has only one element. If there is only one element, then the power set has just two elements. And then indiscrete topology or trivial topology is again the empty set X, empty set, and then the whole set X. So you can see from here, if your set is singleton set, then the discrete topology and the indiscrete topology, they match up. Otherwise, the discrete topology and indiscrete topology may not be equal. Okay, now I'm going to give you one more example of a topology. Uh, Example number 4 is called the finite complement topology. Complement topology. So it's another very popular example of topology. You will see this topology more frequently in our course. Okay, now what is the finite complement topology? Let's say X is our set, given non-empty set, and then now let me define or let me consider the subset of X. Let me consider the collection of the subset of X. Let's say the collection, let me just first write down this collection. let's say our collection is the subset of X. Let me call that subset is U. uh, then U is in this collection if you take the difference of this subset of X with itself. It has to be either a finite set, or that difference of X and U, it has to be the whole set X. So so for the given set, for given non-empty set X, so we are considering the those subset of X. When you take the difference of that subset with X, uh, the resulting set has to be finite, or the whole set X. Then this collection is a topology, which is called the finite complement topology. You can see here this word finite is here, and then also the complement is somewhat related. That's why it's called the finite complement topology. And let me denote this collection using tau suffix f. Okay. uh, then this collection tau f is a topology on X, and it is it is called the finite complement topology. It's called the finite complement topology. Now, if you want, you can check whether this collection, or basically this is the collection of subset of X, such that if you take the set difference of that set with X, it has to be either finite or the whole set X. You can check whether this collection is a topology or not. So let me check quickly here. Let's show this collection of the subset of X is a topology. To show this collection is a topology, we're going to use the definition of topology. So based on the definition of the topology that we discussed earlier, this collection has to satisfy those three properties. And the first one is the empty set, and then the whole set X, they have to be in this collection, and they are in this collection. This is because, now you can see here, if you look at the definition of this collection, this empty set is in this collection. When you take the difference of this set X with the if you take the difference of empty set with X, the result, it has to be either finite or the whole set X. Now if you take the difference of empty set with any set, the result is X. Now this is our second case. That's why the empty set is in this collection, because if I take the difference of this empty set with X, the result is X. And so that is the reason why empty set is in this collection. And also the X is in this collection, or X is in this collection. This is because, let me take the difference of X with itself. So if you take the difference of X with itself, so if you take the difference of any set with itself, the result is empty set. And the empty set is obviously is a finite set. So this X is in this collection, because when you take the difference of this set with itself, we got the result empty set, and the empty set is a finite set. That's why both empty sets and the whole set X, they are in this collection. So this collection satisfy our first property of topology. Okay. Second property. So the second property is arbitrary unions of the elements of this tau f. It has to be in tau f. That means if you pick any number of the elements, or if you pick any elements of tau f, and then if you take their union, the result has to be in tau f. And to prove that one, now let's say union of sorry, this family of the this is the index family of the subset of subset of x, or this is the is let's this we are just taking the collection of the, or the these are the elements of tau f. It says the arbitrary, that's why I'm using this index alpha. So you can call this collection is an indexed family of non-empty elements of this collection tau f. Now here I'm taking the possible elements of the this collection, and I have denoted that collection or that family by using this notation u alpha. Here alpha is the index. So this collection is called an index family, and so this is the index family of the non-empty elements of tau f. Now here what we want to show is, we want to show that, so we want, or if this guy is a topology, then we need to show that the union of u alpha, so that is the arbitrary union. Arbitrary means any number, union of the any number of the elements of tau f. We want to show that this union is in tau f. If we if you can show that this union is in tau f, then this collection satisfy the second property, otherwise not. We want to show that this guy. So in order to show this one, now based on the definition of our collection, if this union is in tau f, then what, then you should be able to prove this one. In order to show this guy is in tau f, so if you take the difference of this set with x, if you take the difference of this union with x, this union, it has to be either finite, or the whole set x. So this is what we want to prove here. Okay, so in order to show that the x minus union of u alpha is either finite or union or the whole set x, we're going to use De Morgan's law. So the De Morgan's law, by, you can say that by De Morgan's law, law, x minus union of u alpha, that's gonna be same as the you take the difference of each u alpha with x and then take the intersection. So if you take the difference of each u alpha with x and then take the intersection of that family, that intersection is going to be same as the difference of x with the union of the family of u alpha. So this is called the De Morgan's law. So you can you may review the De Morgan's law from the fundamental of mathematics or from the proof class, if you are not familiar with the De Morgan's law. Okay, so here this difference is the intersection of this family x minus u alpha. Now you can see here each u alpha is the element of tau f. Now since each u alpha is the element of tau f, so by the definition of tau f, this x minus u alpha, it has to be either finite, this set, this x minus u alpha, it has to be finite, or it has to be x. This is because u alpha is in tau f. So let's say if x minus u alpha is finite, then you take the intersection. If you take the intersection of the finite set, the result is obviously going to be finite. And let's say instead of this x minus u alpha is finite, let's say x minus u alpha is x. Then if you take the intersection of all the x, the result is x. So you can see here this intersection is either going to be finite or the x. That's why x minus u alpha is either finite or x. So since x minus u alpha is either finite or the whole x, so we can say that this implies that the union of u alpha is in tau f. Now here we just prove that that tau f satisfy the second condition of the topology, and also we need to show that the third condition is also true for tau f. So the third condition is finite intersection of the elements of tau f has to be in tau f. That means if you take the finite number of element of the tau f and if you take their intersection, the result it has to be in tau f. For this one, for that, let's say suppose u1, u2. Now we are just taking the finite number of element of tau f. But in second condition, instead of finite, it could be anything, or it could be any family of the this family of the elements of tau f. Let's say these are the element of tau f. Now here, so what we want to show here, the intersection of these ui's, let's say I is from 1 to n, that intersection it has to be in tau f. If this intersection is in tau f, that's what we want. And in order to show this intersection is in tau f, what you need to show is, you need to show that if you take the difference of this intersection from x, then the intersection, sorry, this difference it has to be either finite, this is the definition of the tau f, this difference it has to be either finite or the whole set x. Okay, all right. Now in order to show this difference is a finite or the whole set x, now we going to use De Morgan's law one more times. By De Morgan's law, x minus intersection of I equal to 1 to n ui, so that guy has to be it's going to be same as, what you do is you take the difference of each ui from x and then take the union of those x minus ui. I is from 1 to n. Here in this case those ui's are finite numbers, so this is called the De Morgan's law. So this difference is gonna be same as the union of the difference of those ui's from x. So this is called the De Morgan's law. As I said before, if you are not familiar with De Morgan's law, please review the De Morgan's law from the Fundamental of Mathematics or Probe class. Okay, now here you can see here this guy x minus ui. Since each ui, I is it could be any number between 1 and n. So if we know each ui is in tau f, if each ui is in tau f, then x minus ui it has to be either finite or this guy it has to be either finite or it has to be the whole set x. Now let's say the x minus ui is finite, then you take the union, the finite union of the finite set is gonna be is finite, okay, because there are only finite number of the set, and if you take the union of the finite union of the finite set, that's gonna be finite. And let's say instead of finite, if x minus ui is the whole set x, then if you take the union of those nx, then obviously that guy is going to be x itself. So here we just saw that the right hand side is gonna be either finite or the set x. So same thing with the left side. So this implies that, this intersection I equal to 1 to n ui is in tau f, because when you take the difference of this guy with x, its result is either finite or the x. uh, so here we just saw that this tau f also satisfy the third property of topology, so that this collection tau f is a topology. And like I said earlier, this is a very popular example of topology. You will see this topology more frequently in our course. Okay, now I'm going to give one more definition, then we done for this section. Topological spaces. Few more definition. Let's say X is a set, non-empty set, and tau primes are topologies on the set X. Then so if tau is subset of tau prime, that means if every element of this topology tau, they are also the elements of tau prime. If tau is subset of tau prime, then this tau prime is called, then the tau prime is called, it's called larger topology, or which is also called the finer. It's called finer or larger, and this guy tau is called uh, uh, is smaller or quasar topology. Okay, smaller topology. So if you have two topology on the given set, if one of them is the subset of other, that one is called the smaller or coarser, and then the other one is called the finer or larger. For example, if you go back to the first example of the topology, let me go back to our first topology. In the first example for the topology, you can see we have those three topology here, and then you can see here this tau 1, which is the subset of tau 3, because every element of tau 1 are also the element of tau 3. So we can say that tau 1 is a smaller topology or coarser topology, and the tau 3 is a finer or larger topology. Okay, so in example number 1, tau 1 is a it's a coarser or a smaller topology, and tau 3 is a finer or larger topology, because so you can say tau 1 is the subset of tau 3. One more definition. So here we just learned about the finer and coarser topology. Let's say if you have the given set X, and tau prime are two topology on X, and if you have either tau is subset of tau prime or tau prime is subset of tau, then these two topology are comparable. So if tau is if let's say X is the set, tau and tau prime are the two topology. If tau is subset of tau prime or tau prime is subset of tau, then tau and tau primes are comparable. So that means for the given set, if you have two topology, if those two topologies, if one of them is finer and the other one is coarser, then they are comparable, otherwise not. We have seen that in the given topology you can have more than one topology. So if you have more than one topology, it's not necessarily that those given topologies are always comparable. They may not be comparable. So for example, if you go back to the first example, and you can see that tau 1, since tau 1 is subset of tau 3, and we have already seen tau 1 is the smaller Quasar topology, and tau 3 is the larger finer topology, so tau 1 and tau 3 are comparable. But if you look at the tau 2 and the tau 3, so you can see here tau 2 has this set AB, but tau 3 doesn't, and also tau 3 has this set A, which is not in tau 2. So tau 3 and tau 2, we cannot say tau 3 is the subset of tau 3 or tau 3 is the subset of tau 2. So neither of them are the subset of each other. So tau 2 and tau 3 are not comparable. So that means, so if you have a given topology on the given set, if you have more than one topology in the given set, then is not necessarily those topologies are comparable. So example, you can say that in example 1, tau 1 and tau 3 are comparable, but not tau 2 and tau 3. Okay, all right, so that's all for this section.